Welcome to Academic Catalyst for a fast and efficient learning. Greetings from Academic Catalyst. Today's topic is going to be chemical equilibria. This is part one of a series. There are 4 parts to it. You can look it up for the next few, 2, 3, and 4 later. In this part one, we're going to talk about the basics of chemical equilibrium. So in order to start out with chemical equilibria concept, let's first look at a reversible reaction. When I say a reversible reaction, compound A reacts with compound B to give rise to compound C. Initially, A and B will combine and start making C. But once a critical concentration of C is achieved, then the reaction starts to go back because it has crossed a particular concentration of product. It's no longer stable enough to remain as the product, and it starts to dissociate into the reactants, in this case A and B. This is a reversible reaction. Now, the equilibrium concepts always involve these reversible reactions. Let's take an example here. I have hydrogen gas reacting with iodine gas to give hydrogen iodide. This is also a gas. So we have hydrogen here represented in white, iodine in light purple, and then you have hydrogen iodide, which consists of 1 hydrogen atom and 1 iodide atom. So you can see that initially when we start out the reaction at time 0, we only have hydrogen and iodine. So if you look at a reaction mixture, and you can see that I have time 0 here. So at this point, the reaction hasn't started, and we only have iodine and hydrogen gas, and they are as individual gases. Let's say we let the reaction go on for about 16 minutes. You can see that the clock shows 16 minutes here. And you can now see that we have started forming the product, which is hydrogen iodide. So we have some molecules of the product, and we still have some amount of the reactants, the hydrogen and iodine. They're still present in this reaction mixture. Now let's say we let it go for another 16 minutes. Let's say we have gone about 32 minutes since the start of the reaction. Now you can see that in comparison to the previous time slot, where it was 16 minutes, you can see that now we have a higher number of product. So as the product concentration increases, you can see that the reactant concentration decreases. Law of mass action. So let's say what happens when we go about 48 minutes. So now you can see that when we compare the reaction mixture at 32 minutes versus 48 minutes, you can see that there is not much of a change in the concentration of the reactants or the products. So this is when we say that the system has reached an equilibrium. This is the maximum that the product will be formed under these concentrations of the reactants, is what this says. So which means we can see that at this point, by the time the system reaches an equilibrium, we can say that the concentration of all the reactants and all the products remain constant. They do not change much with time. Bear in mind that this does not mean that the reactant and the product concentrations are equal. They're just constant. In some cases, they can be equal, but it doesn't mean that whenever a system is in equilibrium, the product concentration is equal to reactant concentration. That is not right. Now, the equilibrium is said to be dynamic. What do we mean by the term dynamic right there? So let's look at the reaction mixture. So at 35 minutes, Remember, at 35 minutes, just beyond the 32-minute, we already had reached an equilibrium. So let's say at 40 minutes, there is the reaction went forward and we had more of the product, slightly more than the reaction mixture at 35 minutes. You can see that I have a lot more of the product at 40 minutes. However, this is not stable because the product will start to go back to form the reactant. So the reactant keeps forming the product, but if it crosses a critical concentration, it goes back and it stabilizes at the equilibrium state. This is the equilibrium state. So if you push it further, the tendency is to come back to equilibrium. So essentially, even if you were to go beyond that, it will try to go back into that. At 45 minutes, you can see that it has gone back to the equilibrium state, and that's the most stable state for this reaction. So one example I can give here is, think of it as a pendulum. So a pendulum at equilibrium at rest will be facing down. You perturb it by pushing it either to the left or the right. It goes back and forth until it comes back to the equilibrium state. So the reaction, whenever you perturb it, it wants to come back to equilibrium. The resting state is the equilibrium. And that's how you want to visualize these reactions, as it is trying to get to that equilibrium state. So just to reiterate, at equilibrium, we can say that the concentration of all the reactants and all the products are not changing much, and they can be considered to be constant. So this is what we had after about 48 minutes, the concentration of products and reactants. So if you were to plot the concentration along the y-axis and the time along the x-axis, so we can say that somewhere around here, the system attained equilibrium. So at this point, there is no more change in the concentration. So if the concentrations don't change, that means their ratios will also be constant. And that is how we quantify, and that becomes the equilibrium constant, EQ, KEQ. So remember, this is capital K. The small k is usually referring to rate constant. So let's say for the same example that we just discussed, we are looking at hydrogen reacting with iodine to form hydrogen iodide. Now, if we were to figure out what is the KEQ for this particular reaction, we have to mix the two and wait for the system to reach equilibrium. Once it has reached the equilibrium, then you measure the concentrations of each of the reactants and products at equilibrium. Measure concentrations of each of the reactants and products at equilibrium. Once you measure that, then the ratio of that will become the equilibrium constant. In this case, we have HI. Now the 2HI can be represented as is the same as HI plus HI, correct? So if I were to write it as HI and HI divided by H2 and I2. So when you have two of these, we can square it, and that's where the coefficient becomes the exponent. So you can see that the coefficient in the reaction becomes the exponent term in the expression, K equilibrium. This is called as the equilibrium constant expression. It's always products over reactants. Now, another aspect of equilibrium is the rate. If you're looking at the rate of the reaction, whenever you have like these reactions going on, by the time the system reaches equilibrium, the rate of the forward reaction, so this is the forward reaction, and this is the reverse reaction. So the rate for the forward reaction is given by Kf, and the rate for the reverse reaction is given by Kr. So at equilibrium, Kf is equal to Kr. And that's the reason why the concentration does not change. The reverse reaction and the forward reaction, you can see that the rates will be equal. And that's one way to identify if a system is already at equilibrium. Now, the general expression for KEQ so let's say we have A, B, C, D as our reactants and products. And each of these coefficients show a balanced equation right there. So if you have to write the KEQ for a reaction like this, you can see that each of the product will be raised to the corresponding coefficient, and the denominator will be the reactants. So it's always going to be product concentration, product of the product concentration over product of the reactant concentrations, how many ever we have. Another thing you want to observe here is every time you will see that these reactions will always show the state of matter. Remember, the states of matter will be pure solid, which is shown as small s, pure liquid as small l, gas small g, and aqueous as aq. Now, when we write the expression for the equilibrium here, we only consider the gas and the aqueous states. Pure solids and pure liquids will never appear in our equilibrium expression. Pure solids and pure liquids will not appear in the equilibrium expression. This is one thing to remember, is this is probably going to be one question very likely. Most of the time you will be tested. Given a reaction, they'll ask you to write or identify the correct equilibrium expression. Make sure that you don't consider the pure solids and liquids. However, anytime you have a gas or an aqueous state of matter, then that needs to be considered for the equilibrium expression. So if I were to have something like AA, so let's say we have this equilibrium reaction. So let's say this is gas, this is solid, this is liquid, and this is aqueous. And if you were to be asked to express the equilibrium constant for this reaction, so the KEQ in this case will be, on the product side, we only have the D, so D to the power of D here, divided by, on the reactant side, we only have A, so A to the power of A. Neither B nor C will be considered because they are pure solid and liquid, respectively. So in summary, we can say that reversible reactions can reach equilibrium, and once they reach equilibrium, the rate of forward reaction is equal to the rate of the reverse reaction, and the concentrations of products and reactants remain constant, which is why we can express the KEQ as the product of the product concentrations over the reactant concentrations. Mind you, this has to be measured at equilibrium only, not in the initial, not much later or when you have added something. You have to let the system get into equilibrium and then measure the concentration of the products and then measure the concentration of the reactants and then take the ratio of that in order to obtain the KEQ value. Now, the KEQ is a constant, it's a ratio, so it does not have any units, no units for KEQ. It's just a ratio. And also remember, pure solids and pure liquids do not appear in the equilibrium expression. Well, that's it for this part of chemical equilibrium. Join us for the second, third, and the fourth parts, which will discuss about the factors, the solubility equilibria, and the acid-base equilibria, respectively. Good luck and see you later.